Welcome to Sleep to Science. Tonight, we're diving into the hidden lives of those gentle points of light scattered across our night sky. Most people see peaceful twinkling stars. They imagine cosmic decoration. But what if those innocent lights represent something far more dramatic? Each star you've ever wished upon operates as a massive nuclear furnace. These cosmic engines burn for billions of years. Some live quiet suburban lives like cosmic retirees. Others burn fast and explode with the force of entire galaxies. What determines these wildly different stellar destinies? The answer lies in a single cosmic rule so simple it should be printed on every astronomy textbook cover. Tonight, you'll discover how stellar birth weight determines everything. Lifespan, brightness, death style, all decided by one number, the counterintuitive physics that makes giant stars die young while tiny ones outlast the universe. And the three-stage journey every star must take from birth in frigid gas clouds to final transformation into cosmic ghosts. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe, only if you enjoy these late-night journeys. Now let's begin. Ancient humans created beautiful stories about starlight, holes poked in a cosmic ceiling, distant campfires, maybe the souls of ancestors keeping watch. These romantic ideas lasted for thousands of years. Then we invented powerful telescopes. What astronomers discovered up there should have sent everyone running for cover. Those innocent twinkling stars, they're actually controlled nuclear explosions, every single one. Each stellar core burns at 15 million degrees, hot enough to vaporize your car in a nanosecond. Hydrogen nuclei slam together with incredible force. They fuse into helium. Same process that powers hydrogen bombs, except these cosmic furnaces have been burning continuously for billions of years. Consider this mind-bending scale. A typical star produces energy equivalent to 100 billion hydrogen bombs detonating every second. Our sun converts 600 million tons of hydrogen into helium every second. That's like Earth's entire nuclear arsenal exploding every few heartbeats. This cosmic violence has been running for 4.6 billion years. So how does a star contain this impossible inferno? Think of it as the ultimate cosmic wrestling match. Gravity desperately tries to crush everything inward with unstoppable force. Meanwhile, nuclear fire pushes outward with equal determination. This stellar tug-of-war creates perfect balance. The star maintains its size because these opposing forces exactly cancel each other out. What's truly remarkable is stellar self-regulation. Core gets squeezed harder. Temperature rises, fusion accelerates, more pressure pushes back. Fusion running too hot. Core expands slightly, temperature drops, nuclear reactions slow down. This automatic adjustment lets stars burn steadily for time periods that make human civilization look like a brief cosmic moment. What if your entire biography could be written by weighing you at birth? Career path, lifespan, retirement plan. Everything decided by one measurement. That's exactly how stellar destinies work. In the vast universe where countless variables seem to matter, one simple number determines everything. Mass. The total amount of stellar stuff gathered during formation. This single number writes the star's complete biography with mathematical ruthlessness. A star with 8 times our sun's mass burns out in 40 million years. Then it explodes. Double that mass to 16 solar masses. Lifespan shrinks to just 10 million years. Meanwhile, a red dwarf with half our sun's mass will burn for over 100 billion years. That's longer than the current age of the universe. Your mass at birth determines whether you're living fast or practically immortal. Why does mass control everything so completely? More massive stars crush their cores with exponentially greater force. This drives internal temperatures far beyond what smaller stars can achieve. While our Sun's core reaches 15 million degrees, a massive star maintains core temperatures exceeding 100 million degrees. At these extreme temperatures, nuclear fusion goes absolutely wild. This creates a cosmic paradox that defies common sense. Stars with the most nuclear fuel burn out fastest. Those with the least fuel last longest. Think of it like cosmic economics gone wrong. The richest stars blow through their wealth so recklessly they quickly go bankrupt. Meanwhile, modest stars stretch their resources across cosmic eternities. A massive blue giant might contain 50 times more hydrogen than our Sun. Yet it exhausts this fuel thousands of times faster. The star's birth weight determines its final fate with clockwork precision. Lightweight stars under 8 solar masses become white dwarfs after gently puffing off their outer layers. Medium-weight stars explode as supernova, leaving behind neutron stars. The heavyweight champions exceeding 25 solar masses disappear entirely into black holes. From the moment of birth, each star carries its own cosmic destiny. Stop and think about this for a moment. In every other aspect of life, having more resources means lasting longer. More money equals better retirement. More food means surviving famines. More fuel gets you farther down the road. Stars operate by completely opposite rules. The stellar universe rewards frugality and punishes excess with cosmic cruelty. Red dwarf stars represent the stellar world's ultimate cheapskates. They weigh less than half our Sun's mass, but they burn hydrogen so efficiently they could keep shining for 100 trillion years. That's thousands of times longer than the universe has existed. These cosmic misers burn at such low temperatures their surfaces glow dull red. They're like driving a hybrid car at 35 miles per hour while everyone else races past in gas guzzlers. Meanwhile, blue supergiant stars live like cosmic lottery winners who just discovered their bank account. These stellar behemoths can weigh 50 times more than our Sun. They burn 100,000 times brighter. Their surface temperatures reach 50,000 degrees, hot enough to appear brilliant blue-white. They consume their massive hydrogen reserves so recklessly that 50 solar mass stars burn out in just 4 million years. That's barely enough time for Earth to complete 20 trips around our modest star. The physics behind this paradox involves stellar peer pressure taken to extremes. Massive stars crush their cores so hard that hydrogen fusion runs at ridiculous speeds. Think of it like cosmic road rage. Bigger stars feel compelled to burn faster and brighter than their neighbors. They maintain internal pressures and temperatures so extreme that nuclear reactions proceed thousands of times faster than necessary. This creates the universe's most dramatic tale of haves versus have-nots. Blue supergiants live spectacular but brief lives as cosmic rock stars. They burn bright, live fast, leave behind explosive deaths that light up entire galaxies. Red dwarfs live quiet, modest lives as cosmic hermits. They outlast empires, species, and solar systems through simple conservation. In the stellar universe, slow and steady wins by geological margins. Every star in the universe follows the same basic 3-act drama. Act 1, a birth from cosmic nothingness. Act 2, billions of years maintaining nuclear balance. Act 3, death that ranges from gentle fade-out to cosmic explosions. What makes stellar biographies fascinating is how the same plot gets customized based on birth weight. Act 1 always begins the same way regardless of final stellar size. Somewhere in the cold darkness of space, a giant cloud of hydrogen gas starts feeling gravitational pressure from its neighbors. Maybe a nearby supernova sends shock waves through the cosmic neighborhood. Maybe the cloud simply reaches critical mass after millions of years of gradual growth. Either way, gravity wins its battle against gas pressure. The cloud begins collapsing inward like cosmic quicksand. This gravitational collapse transforms cold gas into stellar rocket fuel through pure physics. As the cloud shrinks, gravitational potential energy converts to heat energy. Temperatures climb from near absolute zero to hundreds, then thousands, then millions of degrees. When the core finally reaches 10 million degrees, hydrogen nuclei possess enough energy to overcome their electrical repulsion. They fuse together. Nuclear ignition marks the official moment of stellar birth. Act 2 represents the star's entire adult life, maintaining perfect cosmic balance. For stars like our Sun, this stable period lasts 10 billion years of steady hydrogen burning. More massive stars rush through their main sequence careers in mere millions of years. During this phase, stars operate as cosmic thermoregulators. They automatically adjust their nuclear burning rates to maintain structural stability against gravitational collapse. Act 3 arrives when stars begin running low on hydrogen fuel in their cores. This is where stellar masses create dramatically different endings. Lightweight stars gently expand into red giants before quietly puffing off their outer layers. They retire as white dwarf stars. Heavyweight stars experience catastrophic core collapse followed by supernova explosions. The most massive monsters collapse directly into black holes. Gravitational prisons so powerful that not even light can escape. Stellar death styles split along mass lines with the precision of cosmic insurance policies. Your stellar birth weight determines not just how long you'll live, but exactly how your cosmic story ends. The universe operates 3 completely different death scenarios depending on whether you're born lightweight, middleweight, or heavyweight. Each category gets its own personalized finale. Lightweight stars under 8 solar masses choose the gentle retirement plan. When core hydrogen runs low, these modest stars expand into red giants. Their outer layers puff outward like cosmic balloons, but they lack the gravitational muscle needed for violent endings. Instead, they quietly shed their outer atmospheres into space over millions of years. This creates colorful planetary nebulas that glow like cosmic flowers. What remains behind is a white dwarf star, essentially the original stellar core, compressed to Earth size. Middleweight stars between 8 and 25 solar masses qualify for the explosive death package. When these stars run out of core fuel, their greater mass allows gravitational collapse to proceed much further. Core temperatures climb so high they can fuse increasingly heavy elements. Carbon into oxygen, oxygen into silicon, silicon into iron. But iron represents the cosmic stopping point. Fusion of iron absorbs energy instead of releasing it. Nuclear burning suddenly stops. Without outward pressure to resist gravity, the entire stellar core collapses in less than 1 second. This triggers a supernova explosion that can outshine an entire galaxy. Heavyweight stellar champions exceeding 25 solar masses qualify for the ultimate cosmic mystery package. These massive stars experience the same core collapse as middleweight stars, but their greater mass allows gravitational crushing to continue past the neutron star stage. Nothing in the known universe possesses enough structural strength to resist this level of compression. The stellar core disappears entirely into a black hole, a region where gravity becomes so powerful that light cannot escape. The remarkable thing about these 3 death scenarios is their complete dependence on stellar birth weight. A star born with 7.9 solar masses becomes a white dwarf. An identical star born with 8.1 solar masses explodes as a supernova. The difference between gentle retirement and cosmic detonation comes down to just 0.2 solar masses. Scattered throughout our galaxy, massive clouds of hydrogen gas drift through space at temperatures barely above absolute zero. These stellar nurseries stretch dozens of light years across, so enormous that light takes decades just to cross from one side to the other. For millions of years, these cosmic maternity wards float peacefully through the darkness. They show no signs of the dramatic transformations waiting inside them. Then something triggers cosmic labor pains. What breaks the peace in these frigid stellar cradles? Sometimes a nearby massive star explodes as a supernova. It sends shock waves racing through the galaxy at thousands of miles per second. These cosmic tsunami waves slam into peaceful gas clouds like depth charges. They suddenly compress regions that had been stable for millions of years. Other times, the clouds simply grow too large for their own gravitational good. They reach critical mass where their own weight becomes too much to support. When gravitational collapse begins, it starts slowly like a cosmic avalanche gathering momentum. Individual hydrogen atoms start falling toward the cloud's densest regions. What begins as gentle inward drift accelerates rapidly. More material joins the cosmic stampede toward the center. Within a few 100,000 years, regions that had been drifting peacefully suddenly contract like cosmic fists clenching shut. The scale of this cosmic construction project defies human comprehension. A typical stellar nursery contains enough raw material to build several hundred stars like our Sun. That represents more matter than exists in 100,000 Earth-sized planets combined. Yet gravity organizes this enormous construction project with mathematical precision. It simultaneously creates multiple stellar building sites within the same cloud system. What's truly remarkable about stellar pregnancy is how it transforms cosmic emptiness into cosmic violence through pure physics. These gas clouds start out so diffuse that laboratory vacuums on Earth contain more matter per cubic inch. Yet within a few 100,000 years, gravitational collapse creates stellar cores with densities exceeding liquid water. The cosmic equivalent of turning nearly perfect emptiness into something denser than the deepest ocean. Here's where stellar construction gets seriously hot and heavy. As that enormous gas cloud collapses under its own weight, something extraordinary happens. Gravity doesn't just squeeze the gas into a smaller space. It transforms gravitational potential energy into thermal energy through one of nature's most elegant heating systems. The cosmic equivalent of converting falling water into steam, except the steam reaches temperatures that would vaporize planets. The physics behind this cosmic heating system operates like a massive celestial engine with no moving parts. Every hydrogen atom falling toward the cloud's center picks up speed due to gravitational acceleration. When these atoms collide with material already packed into the central regions, their kinetic energy converts directly to heat. Billions upon billions of tiny atomic collisions gradually raise the temperature, from near absolute zero toward levels that make blast furnaces look like refrigerators. This gravitational heating process accelerates dramatically as collapse continues. When the gas cloud initially starts contracting, temperatures climb slowly. Temperatures climb from minus 400 degrees Fahrenheit toward merely freezing. But as the core regions become more compressed, the heating rate increases exponentially. Within the final 50,000 years of collapse, core temperatures skyrocket from room temperature to 10 million degrees Celsius. What makes this heating process so efficient is gravity's relentless compression. It creates a cosmic pressure cooker with no safety valve. As more gas falls inward, the core becomes increasingly dense and hot. Higher density means more frequent atomic collisions, which generates more heat, which creates more pressure. This attracts even more material from the outer regions. This runaway heating process continues until the stellar core reaches the magical temperature threshold needed for nuclear fusion. The remarkable thing about this natural heating system is how it creates stellar cores hotter than anything else in our solar system. The Sun's core temperature of 15 million degrees exceeds the surface temperatures of any planet by factors of thousands. Yet this cosmic furnace gets built entirely through gravitational compression. No external energy source required. Gravity essentially converts the enormous potential energy stored in a diffuse gas cloud into thermal energy. That energy powers a nuclear furnace for billions of years. After hundreds of thousands of years of gravitational collapse and heating, something miraculous finally happens in that compressed stellar core. Temperature reaches the critical threshold of 10 million degrees Celsius, hot enough for hydrogen nuclei to overcome their electrical repulsion and fuse together. This represents the single most important moment in any star's entire existence. Nuclear ignition, the instant when a collapsing gas cloud officially becomes a genuine star. Before this moment, the object was just a gravitational heating system slowly cooking itself toward higher temperatures. After nuclear ignition, it becomes a self-sustaining stellar furnace, capable of burning steadily for billions of years. The transition happens surprisingly quickly once the fusion threshold gets crossed. Within just a few thousand years, nuclear burning spreads throughout the central core regions. It establishes the energy production system that will power the star's entire adult life. This nuclear ignition process operates like the universe's most dramatic light switch being flipped on. For hundreds of thousands of years, the forming star remained essentially invisible, a dark blob slowly heating up in the cosmic darkness. Then fusion begins, and suddenly the object starts producing energy at rates that make nuclear weapons look like birthday candles. A newly ignited solar mass star generates power equivalent to 100 billion hydrogen bombs exploding every second. That's enough energy output to supply current human civilization for millions of years. What makes stellar ignition especially remarkable is how it instantly solves the gravitational collapse problem. Nuclear fusion produces enough outward pressure to exactly balance the inward gravitational crush. The star stops collapsing and settles into a stable configuration. Nuclear fire pressure equals gravitational compression pressure. This cosmic balance point can persist for billions of years without adjustment. The newborn star has essentially learned to regulate its own energy output through pure physics. If gravitational pressure increases slightly, core temperature rises, fusion accelerates. Increased outward pressure pushes back. If fusion runs too hot, the core expands slightly, temperature drops. Nuclear burning slows until perfect balance returns. This natural thermostat allows stars to maintain steady energy production across time periods longer than continents take to drift across planetary surfaces. Newborn stars make terrible housekeepers. After spending hundreds of thousands of years carefully gathering cosmic construction materials, they immediately start blowing everything away. These cosmic babies haven't learned proper energy management yet. They produce far more heat and radiation than necessary for simple structural maintenance. The result: stellar wind gusts that would strip the atmosphere off planets, combined with radiation intense enough to evaporate cosmic dust across entire light years. This destructive phase represents stellar adolescence at its most dramatic. Young stars can burn 100 times brighter they will during their mature adult years. They produce radiation so intense it heats and ionizes gas throughout their local neighborhood. They launch high-speed stellar winds racing outward at hundreds of miles per second, fast enough to circle Earth in less than 2 hours. These cosmic gales gradually blow away the leftover gas and dust from the original stellar nursery. The cleanup process creates some of astronomy's most beautiful fireworks displays. As stellar wind and radiation interact with surrounding gas and dust, they sculpt elaborate structures. These cosmic light shows can stretch several light-years across. They remain visible for millions of years as stellar birth announcements broadcast throughout the local galactic neighborhood. What's particularly fascinating about stellar adolescence is how it reveals the new star's future personality. More massive stars throw more violent tantrums. They produce stellar winds so powerful they clear out enormous regions around their birth sites. These cosmic bulldozers can blow away enough material to prevent other stars from forming in their immediate neighborhoods for millions of years. Meanwhile, smaller stars produce gentler cleanup operations. They remove just enough birth material to reveal their stellar surfaces without devastating the surrounding area. This birth material removal serves an important cosmic purpose beyond simple housekeeping. The original gas and dust clouds that surrounded forming stars would block most of their light output if left undisturbed. By blowing away this cosmic packaging, young stars ensure their light can escape into space. They begin their careers as visible stellar residents. The debris removal also helps establish the star's final mass. Once the stellar winds become strong enough to overcome local gravitational attraction, the star's growth phase ends. Its main sequence, adult life, begins. The moment nuclear fusion ignites in a stellar core, cosmic accountants essentially finish writing that star's complete biography. Everything that happens afterward gets determined by one simple measurement made during those first few thousand years of nuclear burning: total mass. The amount of stellar construction material successfully gathered before those powerful stellar winds blow the rest away. This mass-determined destiny operates with the reliability of cosmic clockwork. A star that manages to accumulate 8 solar masses will live exactly 40 million years before exploding as a supernova. Double that mass to 16 solar masses, and the lifespan shrinks to just 10 million years. Meanwhile, a modest red dwarf that collects only half our sun's mass will burn steadily for over 100 trillion years, thousands of times longer than the universe has existed so far. Your stellar birth weight determines whether you're living cosmic fast lane or practically immortal. Why does mass control stellar destinies so completely? More massive stars compress their cores harder, creating higher temperatures that drive nuclear fusion at exponentially faster rates. A solar mass star burns hydrogen at a steady pace. A star 20 times more massive consumes its nuclear fuel like a cosmic speed addict. Higher mass equals higher core pressure equals higher temperature equals faster fusion equals shorter lifespan. The mathematical relationship follows precise laws that work like cosmic insurance actuarial tables. This mass lifespan relationship creates the universe's most counterintuitive economic system. The richest stars always go bankrupt first because they can't control their spending habits. Meanwhile, the most modest stars stretch their limited resources across time periods that span entire galactic civilizations. A massive blue giant might contain 50 times more hydrogen than our sun, yet it exhausts its fuel supply thousands of times faster due to its wasteful burning habits. Stellar economics rewards frugality and punishes excess with mathematical precision. Perhaps most remarkably, the star's birth weight also determines its final fate with binary precision. Stars below 8 solar masses die quietly as white dwarfs after gently puffing off their outer layers. Stars above 8 solar masses explode as supernova and leave behind neutron stars or black holes. The difference between gentle retirement and cosmic detonation comes down to just a few percent difference in birth weight. In the stellar universe, small differences in starting conditions create dramatically different endings. Deep inside our sun's core, the universe's most productive kitchen has been operating nonstop for 4.6 billion years. This stellar cooking operation processes raw ingredients at a scale that would overwhelm any earthly food factory. Every single second, 600 million tons of hydrogen gets converted into helium through nuclear fusion. That's like transforming the mass of a mountain into a slightly smaller mountain, while releasing energy equivalent to billions of hydrogen bombs. This cosmic cuisine has been running the same recipe continuously since before Earth even existed. The scale of this stellar food processing defies human comprehension. In just 1 second, our sun's core processes more raw material than all the food ever produced by human civilization combined. Over the course of a typical day, it converts roughly 50 billion tons of hydrogen into helium, enough material to build several thousand copies of Mount Everest. Yet this represents merely the daily routine for a completely average middle-aged star. It follows a recipe shared by hundreds of billions of stellar neighbors throughout our galaxy. What makes this cosmic cooking so remarkable is the precision required for the basic fusion recipe. 4 hydrogen nuclei must collide and stick together with exactly the right amount of energy. Too little collision energy, and the nuclei bounce apart without fusing. Too much energy, and the reaction proceeds so violently it disrupts the delicate pressure balance. The core temperature of 15 million degrees represents the perfect cooking temperature. It allows fusion to proceed at exactly the right rate. This stellar kitchen operates with efficiency that would impress any chef. The fusion process converts 0.7% of the hydrogen's mass directly into pure energy. That might sound like a tiny percentage, but when multiplied by 600 million tons per second, it produces enormous power. Enough energy to power human civilization at current consumption rates for 500,000 years. Every second, the sun essentially operates as a cosmic power plant that could supply all human energy needs for geological time periods. Perhaps most impressively, this massive cooking operation maintains perfect quality control across billions of years. The stellar core automatically adjusts its fusion rate based on gravitational pressure and temperature conditions. It speeds up production when squeezed harder, and slows down when pressure decreases. This self-regulating kitchen has been producing the exact same energy output needed to maintain stellar stability. It has done this for longer than complex life has existed on Earth. Every star in the universe spends its entire adult life locked in the most epic wrestling match imaginable. In one corner, gravity flexes its muscles as the ultimate cosmic heavyweight champion. It constantly tries to crush the star down to a pinpoint with relentless inward pressure. In the opposite corner, nuclear fusion fights back as the explosive underdog. It pushes outward with the force of billions of hydrogen bombs to prevent gravitational collapse. This stellar smackdown has been running continuously for billions of years. Neither side gains a permanent advantage. What makes this cosmic wrestling match so perfectly balanced? The two opposing forces operate through completely different physical mechanisms that naturally counteract each other. Gravity grows stronger as stellar material gets compressed into smaller spaces. This creates higher density and increased gravitational attraction. Meanwhile, nuclear fusion burns hotter and faster when compressed. This produces more outward pressure to resist gravitational crushing. These opposing trends create a natural equilibrium point where inward gravitational force exactly equals outward nuclear pressure. This stellar balance operates with precision that would impress any tightrope walker. If gravity gains even a slight advantage, the star contracts slightly, core temperature rises, fusion accelerates, increased pressure pushes back until equilibrium returns. If nuclear pressure becomes too strong, the star expands slightly, core temperature drops, fusion slows down, gravitational pressure reasserts control. This automatic balancing system allows stars to maintain the same size and energy output across time periods longer than continents take to drift. The remarkable stability of this cosmic wrestling match becomes apparent when you consider the extreme forces involved. Our Sun's core experiences gravitational pressure 200 billion times greater than Earth's atmospheric pressure. It is enough to crush any known material into subatomic particles. Yet nuclear fusion generates exactly the right amount of outward pressure to resist this crushing force. It maintains stable stellar structure. The balance point between these enormous opposing forces remains steady to within fractions of a percent across billions of years. What happens when this perfect wrestling match finally ends? The outcome depends entirely on stellar mass and available nuclear fuel supplies. When hydrogen fuel begins running low in stellar cores, fusion pressure starts losing the wrestling match against gravity. For smaller stars, this leads to gentle expansion into red giants. For larger stars, it triggers catastrophic collapse followed by supernova explosions. But during their main sequence adult lives, stars maintain this gravitational nuclear equilibrium with remarkable reliability. As stars age gracefully through their billion-year adult lives, something fascinating happens to their internal architecture. What starts as a relatively simple two-zone structure gradually transforms into an elaborate multi-story cosmic mansion. Hot fusion core surrounded by cooler outer layers becomes increasingly complex. Think of it as stellar urban planning that creates distinct neighborhoods serving specialized functions. Each zone develops its own character as the star matures. The remodeling process begins slowly during the star's early adult years. Nuclear fusion gradually changes the chemical composition of the core regions. Fresh hydrogen gets converted into helium ash, but this stellar waste product doesn't just disappear. Helium nuclei are heavier than hydrogen nuclei, so they settle toward the center. Fresh hydrogen from outer layers gets drawn inward to fuel continued fusion reactions. Over hundreds of millions of years, this chemical sorting creates distinct compositional zones. Eventually, the accumulating helium ash in the stellar core reaches levels that start affecting the star's internal thermostat. Helium doesn't fuse at the same temperatures as hydrogen. Regions rich in helium ash burn differently than fresh hydrogen zones. This creates temperature gradients that drive circulation patterns throughout the stellar interior. The star develops an internal weather system that transports heat, chemical elements, and nuclear reaction products between different architectural zones. For more massive stars, this interior remodeling becomes truly spectacular as they age into their stellar golden years. These cosmic mansions eventually develop multiple fusion zones operating simultaneously. Like floors in a nuclear-powered skyscraper, the basement burns hydrogen into helium. The next floor up burns helium into carbon. Higher floors fuse carbon into oxygen, oxygen into silicon, and silicon into iron. Each floor operates at different temperatures and pressures while contributing to the overall structural stability. This layered internal structure creates older stars that operate like cosmic chemical factories. Different zones manufacture different elements through nuclear fusion while maintaining overall energy balance. The star essentially becomes an element synthesis corporation that produces increasingly heavy nuclei. This stellar maturation process prepares the star for its eventual contribution to galactic chemical evolution. Stellar winds or supernova explosions later distribute these manufactured elements throughout the cosmic neighborhood. Hidden deep inside aging stellar cores, the universe operates its most productive element manufacturing plants. These cosmic factories don't just burn fuel for energy, they actively create brand new types of atoms. These are atoms that never existed before in the universe's early history. What starts as simple hydrogen and helium gradually gets cooked into the entire periodic table. It happens through nuclear fusion assembly lines that build increasingly complex atomic nuclei step by step, like cosmic Leo construction sets. The element manufacturing process follows strict cosmic assembly line protocols. First shift burns hydrogen into helium during the star's main adult life. When hydrogen supplies run low in the core, temperatures and pressures climb high enough to ignite second shift operations. These fuse helium into carbon through a remarkably precise three-body collision process. 3 helium nuclei must collide almost simultaneously to stick together and form carbon. A nuclear choreography so unlikely it was once thought impossible. But stars proved they could master this cosmic dance across billions of years. More massive stellar factories can operate even more sophisticated production lines as they mature into heavy element specialists. Third shift operations fuse carbon into oxygen and neon. Fourth shift burns oxygen into silicon and sulfur. The final production line fuses silicon into iron, the element that represents the absolute end of profitable nuclear manufacturing. Every fusion reaction up to iron releases energy, but fusion beyond iron actually consumes energy instead of producing it. Iron represents the cosmic stopping point where stellar element factories must shut down their nuclear assembly lines. What makes stellar element synthesis truly remarkable is how it creates cosmic supply chains that span generations of stars. The carbon, oxygen, and silicon produced by previous stellar generations become raw material for planetary construction projects throughout the galaxy. The calcium in your bones, the oxygen you breathe, and the iron in your blood all represent products manufactured inside stellar cores. These cores lived aged and died billions of years before our solar system even formed. Every breath you take contains atoms that were fusion forged in stellar factories scattered across the galaxy. This element manufacturing process also explains why the universe becomes more chemically interesting as it ages. Early galaxies contained only hydrogen and helium because first-generation stars hadn't yet had time to cook heavier elements. Modern galaxies contain rich mixtures of carbon, oxygen, silicon, and iron. This is because successive stellar generations have been operating their element factories for over 13 billion years. Stars essentially serve as cosmic alchemists. They transform the universe's simple initial chemistry into the complex chemical diversity needed for planetary formation, geological processes, and biological evolution. After billions of years of steady nuclear burning, even the most reliable stellar engines eventually face the cosmic equivalent of running low on gas. The hydrogen fuel that has powered the star's adult life begins running scarce in the core regions. Nuclear fusion operates most efficiently where hydrogen concentrations remain high. This stellar midlife crisis marks the beginning of the end. Billions of years of perfect gravitational nuclear balance start shifting toward the dramatic finale. That finale will determine the star's ultimate cosmic legacy. The fuel shortage doesn't happen suddenly like running out of gasoline on a highway. Instead, stellar engines experience a gradual performance decline as core hydrogen concentrations drop below optimal fusion levels. Nuclear burning continues, but less efficiently as the remaining fuel gets diluted with helium ash from previous fusion reactions. The star's energy output begins fluctuating as its nuclear thermostat struggles to maintain steady power production. It is working with increasingly poor fuel quality. These early signs of stellar aging can persist for millions of years before critical system failures begin. What happens next depends entirely on stellar mass and the star's ability to access backup fuel supplies. Smaller stars lack the gravitational muscle needed to compress their cores hot enough for advanced fusion reactions. They're essentially stuck burning hydrogen until supplies run too low to maintain nuclear ignition. After that, they begin the gradual cooling process toward white dwarf retirement. These modest stars face cosmic old age with limited options for extending their energy-producing careers beyond their main hydrogen-burning phase. More massive stars possess enough gravitational compression power to ignite backup fusion systems. These systems burn helium, carbon, and heavier elements in succession. But these advanced nuclear reactions operate much less efficiently than hydrogen fusion. They burn through fuel reserves at dramatically accelerated rates. A star that burned hydrogen steadily for 10 million years might exhaust its helium fuel in just 1 million years. Then it burns through carbon reserves in mere thousands of years. Each successive fuel source burns faster and less efficiently than the previous one. This accelerating fuel consumption creates stellar panic that builds toward catastrophic system failure. As nuclear fuel supplies dwindle, the star loses its ability to maintain the outward pressure needed to resist gravitational collapse. The perfect wrestling match between gravity and nuclear pressure that maintained stellar stability for billions of years finally tips decisively toward gravitational victory. What happens next depends on whether the star has enough mass. Enough mass can trigger runaway nuclear burning or catastrophic core collapse. Somewhere around 8 times our Sun's mass lies the universe's most important cosmic retirement threshold. This invisible boundary line determines whether a star gets to enjoy billions of years of peaceful golden years, or faces catastrophic workplace termination with explosive severance packages. Stars born just slightly below this mass limit follow one career path toward gentle white dwarf retirement. Stars born just slightly above it follow a completely different trajectory toward violent supernova endings. The difference between cosmic social security and cosmic detonation is tiny. It comes down to less mass variation than exists between a compact car and a pickup truck. Why does this particular mass boundary create such dramatically different stellar retirement plans? The answer lies in gravitational muscle and the star's ability to access advanced nuclear fuel sources during its final years. Lightweight stars under 8 solar masses simply lack the gravitational compression power needed to ignite helium fusion in their cores. When hydrogen supplies run low, they're stuck with basic nuclear retirement benefits. That provides enough energy for gradual expansion, but not enough for continued high-energy stellar careers. Meanwhile, heavyweight stars above 8 solar masses possess enough gravitational force to compress their cores hot enough for advanced nuclear burning. When core hydrogen runs low, these stellar powerhouses simply switch to backup fusion systems. They burn helium, then carbon, then oxygen, then silicon in rapid succession. Each fuel source burns faster and hotter than the previous one. This creates an accelerating energy production schedule that leads inevitably toward catastrophic nuclear system failure. This mass-determined retirement system operates with the precision of cosmic actuarial tables. A star born with 7.9 solar masses will expand into a red giant. It will gently puff off its outer layers over millions of years. then settle into white dwarf retirement for billions of years of gradual cooling. An almost identical star born with 8.1 solar masses will burn through increasingly exotic fuel sources for a few million years, then experience total core collapse followed by supernova explosion in less than 1 second. The 0.2 solar mass difference between these outcomes represents less than the mass of Jupiter. What makes this cosmic retirement threshold even more remarkable is how it divides stellar populations throughout the entire galaxy. It splits stellar populations throughout the entire galaxy. Roughly 95% of all stars fall below the 8 solar mass boundary and qualify for gentle white dwarf retirement plans. Only about 5% exceed this threshold and face explosive supernova endings. Yet this small minority of heavyweight stars produces most of the heavy elements scattered throughout the galaxy. It also triggers the shock waves that compress gas clouds to form new stellar generations. The cosmic retirement system rewards the modest majority with longevity. It assigns the dramatic minority responsibility for galactic chemical evolution. When modest stars under 8 solar masses start running low on core hydrogen fuel, they choose gradual retirement with full pension benefits. These stellar retirees don't face sudden termination or explosive workplace accidents. Instead, they begin a gentle transition toward reduced energy production that can last millions of years, while maintaining enough nuclear burning to support comfortable expansion into red giant status. Think of it as stellar social security that provides steady income during an extended retirement phase. The retirement process begins when core hydrogen supplies drop below sustainable fusion levels, unable to access the advanced nuclear fuel sources available to more massive stars. These lightweight stellar retirees start burning hydrogen in shell regions. These shells surround their helium-rich cores. This shell burning operates less efficiently than core fusion, but it produces enough energy to cause gradual expansion. What was once a compact, hot stellar surface slowly inflates into a cooler, larger red giant. It can grow to hundreds of times its original size. During this red giant phase, aging stars essentially become cosmic hot air balloons. They have extremely thin outer atmospheres, supported by nuclear shell burning far below their expanded surfaces. The star's total energy output actually increases during early retirement as shell burning compensates for reduced core fusion efficiency. But this expanded stellar atmosphere becomes so diffuse that surface temperatures drop dramatically. This causes the star's color to shift from hot white or yellow toward cooler orange and red hues. Eventually, even shell burning becomes unsustainable as nuclear fuel supplies continue declining. When this happens, lightweight stars begin the final phase of their retirement. They gently shed their expanded outer atmospheres into space. This mass loss process creates beautiful planetary nebulas, colorful shells of glowing gas. They expand outward at tens of miles per second while remaining illuminated by the hot stellar core left behind. These cosmic light shows can remain visible for tens of thousands of years as stellar retirement announcements. What remains after this gentle atmospheric shedding represents the ultimate stellar retirement outcome. The original stellar core, now stripped of its outer layers, becomes a white dwarf star roughly the size of Earth. It contains most of the original star's mass. This incredibly dense stellar retiree slowly cools over billions of years like a cosmic ember gradually fading in the darkness. White dwarfs represent stellar retirement success stories that can outlast the main sequence lifetimes of dozens of stellar generations. Massive stars above 8 solar masses face workplace termination so violent it makes controlled demolitions look like gentle renovations. These stellar heavyweights can't choose peaceful retirement because their enormous gravitational weight creates core pressures that trigger runaway nuclear reactions. This leads inevitably toward catastrophic system failure. When heavyweight stars run out of sustainable fuel sources, they don't fade quietly into cosmic retirement. They explode with the force of 10 billion suns in supernova detonations visible across intergalactic distances. The path toward explosive termination begins when these massive stars exhaust their core hydrogen supplies and start accessing backup nuclear fuel systems. Unlike lightweight stars that can only burn hydrogen efficiently, heavyweight stars possess enough gravitational muscle to compress their cores hot enough for helium fusion. Then they ignite carbon fusion, then oxygen fusion, then silicon fusion in rapid succession. But each advanced fuel source burns much faster than the previous one. This creates an accelerating countdown toward inevitable nuclear system failure. This accelerating fuel consumption creates stellar panic that builds exponentially as the star ages. A massive star might burn hydrogen steadily for 10 million years, then exhaust helium reserves in just 1 million years, burn through carbon supplies in 1,000 years, consume oxygen fuel in 6 months, and blast through silicon reserves in just 2 weeks. The final fusion processes occur so rapidly they essentially represent controlled nuclear explosions. They are maintained only by enormous gravitational pressure, keeping the stellar core from flying apart. The explosive ending arrives when silicon fusion produces iron in the stellar core. Iron represents the absolute end of profitable nuclear burning because fusion of iron nuclei consumes energy instead of producing it. When iron concentrations reach critical levels, nuclear fuel burning suddenly stops completely. Without outward nuclear pressure to resist gravitational collapse, the entire stellar core implodes catastrophically in less than 1 second. Core collapse releases gravitational energy equivalent to 100 times the star's total main sequence energy output. It is concentrated into a time span shorter than a human heartbeat. This core collapse triggers shock waves that race outward through the star's outer layers at 10,000 miles per second, heating stellar material to billions of degrees. It creates nuclear reactions that produce more energy in a few seconds. That is more energy than our Sun will generate during its entire 10 billion year main sequence lifetime. The resulting supernova explosion completely destroys the original stellar structure. It also creates a cosmic lighthouse that can outshine an entire galaxy containing 100 billion stars. These explosive workplace terminations scatter most of the star's mass throughout the surrounding cosmic neighborhood. They leave behind either a neutron star or black hole as the compressed remnant. Stars don't die without sending cosmic warning signals that astronomers can detect millions of years before the final stellar performance. These dying stellar giants broadcast their approaching end through changes in brightness, color, and energy output. These serve as cosmic obituary announcements visible across galactic distances. Learning to read these stellar warning signs allows astronomers to predict which stars will explode as supernova. It also shows which will fade quietly into white dwarf retirement long before their final acts actually occur. The most obvious warning signal comes from dramatic changes in stellar brightness and color as aging stars struggle with fuel supply problems. Stars approaching the end of their main sequence lives often become variable stars. They fluctuate in brightness as their nuclear thermostats struggle to maintain steady energy production with declining fuel quality. Red supergent stars like Betelgeuse display brightness variations spanning factors of 10 or more. Internal convection patterns bring hot material from deep interior zones to stellar surfaces. cooler material sinks back toward nuclear burning regions. Surface temperature changes provide another reliable warning system for impending stellar death. Stars entering their final evolutionary phases often expand dramatically as nuclear shell burning replaces efficient core fusion. This causes surface temperatures to drop while total energy output increases. This creates the characteristic red color of dying stellar giants whose surfaces have cooled from thousands of degrees to mere hundreds of degrees above room temperature. The transition from hot blue or white surfaces to cool red surfaces signals that stellar cores have begun the nuclear fuel shortage that leads toward final collapse or explosion. Mass loss rates accelerate dramatically as stars approach their final years. This creates stellar wind speeds that can exceed 100 miles per second. It can also eject material equivalent to Earth's mass every few years. These powerful stellar winds strip away outer atmospheric layers and create expanding shells of gas and dust around dying stars. These shells glow with characteristic colors when illuminated by intense ultraviolet radiation from hot stellar cores. Advanced space telescopes can detect these circumstellar shells around stars that will explode as supernova within the next few million years. Perhaps most ominously, some massive stars develop erratic nuclear burning patterns that create brief episodes of dramatically increased energy output. These are followed by periods of reduced brightness. These nuclear hiccups represent trial runs for the catastrophic core collapse that will eventually trigger supernova explosions. Stars like Eta Carina have experienced multiple outbursts during the past few centuries. They ejected material equivalent to several solar masses while temporarily becoming some of the brightest stars visible in Earth's sky. These stellar temper tantrums serve as cosmic smoke detectors. They warn that catastrophic nuclear system failure could occur at any time during the next million years. Aging stars face the same unfortunate reality as middle-aged humans. When their metabolism slows down, they start putting on weight in all the wrong places. Except stellar middle age spread operates on a scale that would terrify any fitness instructor. When core hydrogen fuel begins running low, modest stars like our Sun don't simply shrink and fade away. Instead, they balloon outward to hundreds of times their original size. Their surface temperatures drop dramatically. This creates cosmic senior citizens with seriously expanded waistlines. This stellar weight gain happens through a counterintuitive process that defies everyday expectations about fuel shortages. You'd expect a star running low on nuclear fuel to shrink and dim like a dying campfire. Instead, the opposite occurs. As core fusion slows down due to hydrogen depletion, the star's core actually contracts under gravitational pressure. This core compression heats surrounding hydrogen-rich layers hot enough to ignite shell burning around the depleted core region. Shell burning operates like a cosmic space heater. It actually produces more total energy than the original core fusion ever did. This increased energy output forces the star's outer layers to expand dramatically outward like a balloon being inflated from the inside. What was once a compact, hot stellar surface slowly puffs up into an enormous, diffuse atmospheric envelope that can grow large enough to engulf entire planetary orbits. Our Sun will eventually expand to over 100 times its current diameter. Its surface would reach halfway to Earth's current orbit. The expansion process transforms stellar surfaces from blazing hot furnaces to relatively cool, comfortable temperatures that wouldn't immediately vaporize visiting spacecraft. Red giant surface temperatures drop from 6,000 degrees to around 3,000 degrees. Still hot enough to melt copper, but dramatically cooler than main sequence stellar surfaces. This temperature drop causes the characteristic color change from brilliant white or yellow to the deep orange-red hues that give these expanded stellar seniors their descriptive name. What makes stellar middle age spread especially remarkable is how it actually makes aging stars more luminous. This is true despite their cooler surface temperatures. The enormous increase in surface area more than compensates for lower temperature. This causes red giants to shine 100 to 1,000 times brighter than their compact main sequence predecessors. These cosmic seniors essentially trade stellar fitness for stellar brightness. They become the galactic equivalent of distinguished elderly professors. Their wisdom and experience more than compensate for their expanded physical dimensions. When elderly red giant stars finally decide they've carried enough atmospheric baggage, they begin creating some of the universe's most spectacular art installations. They gently puff their outer layers into space. This cosmic redecorating project produces planetary nebulas. These are colorful shells of glowing gas that expand outward like slow-motion fireworks displays. They remain illuminated by the hot stellar core left behind. Think of it as stellar feng shui that clears away cosmic clutter. It also creates beautiful light sculptures. These can remain visible for tens of thousands of years. The artistic creation process begins when red giant stars can no longer maintain their enormously expanded atmospheric envelopes. Shell burning becomes increasingly unstable during the final stages of stellar evolution. This creates periodic episodes of increased energy output. These push outer atmospheric layers beyond the star's gravitational control. These gentle stellar burps eject material at speeds of 10 to 30 miles per second, fast enough to escape stellar gravity, but slow enough to create graceful, organized outflow patterns rather than violent explosions. What makes these cosmic art projects so visually spectacular is the interaction between ejected stellar material and intense ultraviolet radiation. This radiation comes from the hot white dwarf core left behind after atmospheric shedding. This stellar UV spotlight ionizes hydrogen, helium, and other elements in the expanding gas shell. It causes them to glow with characteristic colors that depend on their chemical composition. Hydrogen glows red. Oxygen produces green and blue hues, while nitrogen contributes purple and violet colors. These combine to create cosmic stained glass windows spanning several light years across. Each planetary nebula develops its own distinctive artistic signature. This depends on stellar rotation, magnetic fields, and asymmetric mass loss patterns during the red giant phase. Some create perfect spherical shells that expand uniformly in all directions like cosmic soap bubbles. Others develop bipolar structures with jets of material streaming outward from stellar poles. Denser equatorial regions create distinctive hourglass or butterfly patterns. The most complex nebulas display multiple concentric shells. These are created by different episodes of mass loss separated by thousands of years. These stellar art installations serve as cosmic galleries. They showcase the chemical compositions of their parent stars. They also provide raw materials for future stellar and planetary construction projects. The carbon, oxygen, and nitrogen distributed through planetary nebula expansion represents processed stellar material that gets recycled into new star formation regions throughout the galaxy. Ancient stellar artists essentially donate their atmospheric collections to cosmic museums. These remain on display for tens of thousands of years. They slowly mix their chemical contributions into the galactic medium. After shedding their atmospheric wardrobes and creating beautiful planetary nebula art projects, aging stars settle into the longest retirement phase in cosmic history. What remains after all the dramatic expansion and mass loss episodes is a white dwarf star. It is essentially the original stellar core stripped down to its bare essentials. It is compressed to roughly Earth size while retaining most of the star's original mass. These stellar retirees then begin cooling processes so gradual they make geological time scales look like brief moments. White dwarf retirement operates on time scales that humble human imagination. A typical white dwarf starts its post-stellar career with surface temperatures around 100,000 degrees. Hot enough to glow brilliant white and illuminate any remaining planetary nebula material. But with no internal nuclear burning to generate fresh heat, these stellar embers can only cool through thermal radiation. That slowly carries away their stored heat energy into space. This cosmic cooling process proceeds so gradually that white dwarfs remain hot enough to glow visibly for over 10 billion years. The cooling timeline for white dwarf retirement makes main sequence stellar lifetimes look like brief career phases. Our Sun will spend about 10 billion years burning hydrogen during its main sequence career. Then perhaps 1 billion years as a red giant. After that, it settles into white dwarf retirement that will last over 100 billion years. That's longer than the current age of the universe by factors of 10. White dwarf retirement essentially represents the permanent storage phase for stellar cores. That will outlast the main sequence lifetimes of dozens of future stellar generations. What makes white dwarf cooling so remarkably slow is the incredible efficiency of their compressed stellar material for storing thermal energy. These stellar retirees pack roughly 2/3 of our Sun's mass into a volume the size of Earth. This creates matter densities where 1 teaspoon of white dwarf material would weigh as much as a car. This ultra-compressed stellar material possesses enormous heat capacity. It allows it to radiate energy for billions of years. It cools very gradually from white-hot temperatures through yellow, orange, and red phases toward eventual darkness. The final stages of white dwarf cooling extend into cosmic time periods so vast they represent pure theoretical speculation. After 100 billion years of gradual cooling, these stellar embers will become brown dwarfs too cool to emit visible light. After trillions of years, they'll fade to black dwarf status. These are invisible stellar corpses drifting through the galaxy like cosmic ghosts. They mark the locations where ordinary stars once burned brightly. White dwarf retirement essentially transforms stellar cores into permanent cosmic monuments. They will outlast entire galactic civilizations. They also serve as long-term repositories for the nuclear processing achievements of previous stellar generations. Imagine compressing every car, building, and person on Earth into a single teaspoon. That's roughly equivalent to the density achievement of white dwarf stars. These are cosmic weight loss success stories so extreme they redefine the meaning of compact stellar packaging. These stellar diet champions manage to squeeze roughly 2/3 of our Sun's mass into volumes smaller than our home planet. This creates matter densities that make lead feel as light as styrofoam by comparison. The compression mathematics behind white dwarf density achievements would impress any physics professor. A typical white dwarf packs about 600,000 Earth masses worth of stellar material into a sphere roughly 8,000 miles in diameter. Slightly smaller than Earth itself. This creates average densities around 1 million grams per cubic centimeter, or roughly 1 million times denser than water. A sugar cube made of white dwarf material would weigh about 1,000 tons, equivalent to a fully loaded freight train compressed into something small enough to hold in your hand. This extreme compression occurs because white dwarfs represent stellar cores that have been crushed by their own gravity. This continues until atomic structure essentially collapses. Normal matter consists mostly of empty space between atomic nuclei and electrons. But white dwarf compression squeezes this atomic architecture until electrons get packed into every available quantum mechanical space. The result is degenerate matter. This is a quantum physics state where electrons resist further compression through pure quantum mechanical principles rather than normal atomic forces. White dwarf surfaces experience gravitational fields so intense they would crush any ordinary matter into subatomic particles within microseconds. Surface gravity on a typical white dwarf exceeds Earth's gravity by factors of 100,000 to 1 million. A person standing on a white dwarf surface would weigh roughly 100,000 tons. They would experience tidal forces strong enough to stretch them into cosmic spaghetti. Then vaporization by 100,000 degrees surface temperatures would complete the destruction process. These stellar diet champions create gravitational environments so extreme they represent natural physics laboratories. They allow study of matter under conditions impossible to recreate on Earth. Perhaps most remarkably, white dwarf compression creates objects so dense that their gravitational fields noticeably bend light and slow down time. According to Einstein's relativity principles, clocks run measurably slower in white dwarf gravitational fields. Light climbing out of these gravitational wells loses energy and shifts toward redder colors. White dwarfs essentially serve as cosmic examples of extreme physics. Quantum mechanics, general relativity, and thermodynamics all combine here. They create stellar objects that push the boundaries of matter density. They remain stable for time periods longer than the age of the universe. Our Sun has already reached stellar middle age at 4.6 billion years old. This means it faces a clearly predictable retirement timeline that astronomers can map with remarkable precision. In roughly 5 billion years, our reliable neighborhood star will begin its transition from steady main sequence burning toward the red giant expansion phase. This fundamentally reshapes our entire solar system. This solar retirement planning affects every planet in our cosmic neighborhood. But Earth faces particularly dramatic changes during our star's golden years. The solar retirement process begins gradually with increased luminosity. This happens as core hydrogen supplies start running low and shell burning becomes more prominent. Over the next billion years, solar energy output will increase by roughly 10%. This is due to core compression and shell burning efficiency improvements. This seemingly modest brightness increase will trigger catastrophic climate changes on Earth. Average global temperatures rise high enough to boil away our oceans. They also strip away our atmospheric water vapor into space. Earth essentially becomes Venus-like long before our Sun even begins its red giant expansion phase. When solar red giant expansion finally begins in earnest, the results become truly spectacular from any surviving planetary perspectives. Our Sun will grow large enough that its outer atmosphere reaches roughly Mercury's current orbital distance. It will completely engulf our innermost planet. It will subject it to stellar interior conditions that vaporize rocky material into constituent atoms. Venus likely suffers the same fate as solar expansion continues. This leaves behind only trace amounts of heavy elements mixed into our Sun's greatly expanded outer atmosphere. Earth's fate during solar red giant expansion depends on complex interactions between stellar mass loss and orbital mechanics. These remain difficult to predict precisely. Our Sun will lose roughly 30% of its mass during red giant and planetary nebula phases. This causes all planetary orbits to expand outward due to weakened gravitational attraction. Earth might migrate far enough outward to avoid direct engulfment by solar red giant atmosphere, but surface temperatures will still climb high enough to melt solid rock. They create global magma oceans that persist for millions of years. The final phase of solar evolution creates an entirely different cosmic neighborhood. It is centered around a white dwarf star with roughly 60% of our Sun's current mass. Any planets that survive red giant expansion will orbit this stellar ember in a frozen solar system. White dwarf luminosity provides less heating than full moonlight currently delivers to Earth's surface. Mars, Jupiter, Saturn, and the outer planets might survive this cosmic transition largely intact. This creates a memorial solar system where frozen worlds orbit the compressed remains of our once brilliant star. It lasts across time periods longer than complex life has existed anywhere in the known universe. Deep inside the cores of massive stars, nuclear fusion operates like a cosmic assembly line that builds increasingly heavy elements through successive burning phases. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, oxygen into silicon. Each step releasing energy that keeps the stellar furnace running and prevents gravitational collapse. But this nuclear construction project eventually reaches a cosmic dead end that spells immediate doom for any star massive enough to get there. That dead end is iron. Iron represents the ultimate cosmic roadblock because of how nuclear physics operates at the atomic level. Every fusion reaction up to iron releases energy when lighter nuclei combine to form heavier ones. This energy release powers stellar cores and provides the outward pressure needed to resist gravitational collapse. But iron sits at the absolute peak of nuclear stability, the sweet spot where atomic nuclei are so tightly bound that fusion reactions involving iron actually consume energy instead of producing it. When stellar cores start producing significant amounts of iron, nuclear fusion suddenly stops being profitable and becomes an energy drain. The iron formation process happens with terrifying speed in massive stellar cores during their final hours. Silicon burning, the last profitable fusion reaction, produces iron group elements so rapidly. Stellar cores can accumulate iron masses equivalent to our entire Sun within just days or weeks. This iron accumulation creates a nuclear poison that gradually shuts down energy production throughout the core region. What was once a vigorous nuclear furnace generating outward pressure becomes a cosmic energy vacuum that actually consumes power while contributing nothing to stellar support against gravitational collapse. When iron concentrations reach critical levels in stellar cores, the cosmic equivalent of sudden cardiac arrest occurs within seconds. Nuclear burning stops completely throughout core regions larger than Earth itself. Without outward nuclear pressure to resist gravity, core material begins falling inward at speeds approaching 70,000 miles per second, roughly 1/4 the speed of light. The stellar core essentially commits suicide by creating the very element that makes continued nuclear burning impossible. This iron-triggered core collapse represents one of the most dramatic phase transitions in the known universe. In less time than it takes to read this sentence, a stellar core larger than Earth compresses. It goes from normal stellar densities to neutron star densities, exceeding nuclear physics limits. The gravitational energy released during this collapse equals the total energy output our Sun will produce. It is spread across its entire 10 billion year main sequence lifetime, except this enormous energy release occurs in less than 1 second. Iron formation doesn't just end stellar nuclear burning. It triggers the most violent explosions in cosmic history through pure gravitational physics operating on stellar mass scales. When iron poisoning finally stops nuclear fusion in massive stellar cores, what happens next defies human comprehension for both speed and violence. The entire stellar core, a sphere of matter larger than Earth and more massive than our Sun, collapses catastrophically in less time than a single human heartbeat. This represents gravitational implosions so rapid and complete it creates some of the most extreme physical conditions possible anywhere in the universe. Core collapse begins slowly by stellar standards, but accelerates exponentially as gravity gains the upper hand over nuclear pressure. Within the first few milliseconds, core density climbs from normal stellar values to densities exceeding solid rock. The collapsing core heats up dramatically as gravitational potential energy converts to thermal energy. But even temperatures reaching billions of degrees can't restart nuclear fusion quickly enough to halt the runaway collapse process. As core density continues climbing toward values that challenge the fundamental structure of matter itself, atomic nuclei get crushed together so violently that protons and electrons are forced to combine into neutrons through pure pressure. This neutronization process essentially erases normal atomic structure throughout the collapsing core, transforming ordinary stellar material into a bizarre state of matter where neutrons pack together like cosmic ball bearings with no empty space between them. For stellar cores below roughly 25 solar masses, neutronization provides enough resistance to halt gravitational collapse. When core density reaches nuclear physics limits around 500 million tons per cubic inch, the core literally bounces when it hits these density limits, creating shock waves that race outward through the star's outer layers at 10,000 miles per second. What remains of the original stellar core becomes a neutron star. It is a cosmic ball bearing roughly 12 miles across but containing more mass than our entire Sun. But for the most massive stellar cores, exceeding 25 solar masses, even neutron degeneracy pressure can't resist gravitational collapse. Core compression continues past neutron star densities toward gravitational conditions so extreme they warp space-time itself into a cosmic trap where not even light travels fast enough to escape. The stellar core essentially disappears from the visible universe, leaving behind a black hole, a region of space-time so gravitationally distorted that it creates a one-way cosmic drain from which nothing can return. When core collapse shock waves finally reach stellar surfaces and break through into space, they create cosmic explosions so brilliant they can be seen across intergalactic distances. A single supernova explosion releases more energy in a few seconds than our Sun will produce. It is spread across its entire 10 billion-year main sequence career. These stellar detonations become so bright they can temporarily outshine the combined live 100 billion stars in their host galaxies, creating cosmic searchlights visible across billions of light years. The energy released during supernova explosions operates on scales that humble human imagination. Core collapse liberates gravitational binding energy equivalent to converting several solar masses directly into pure energy. Through Einstein's mass-energy equation, most of this energy initially appears as neutrinos, ghostly particles that interact so weakly with matter. They could pass through solid lead barriers, several light years thick without stopping. Yet even the tiny fraction of core collapse energy that couples to stellar material creates explosive violence beyond anything else in the known universe. When shock waves from core collapse finally break through stellar surfaces, they accelerate ejected material to speeds exceeding 10,000 miles per second, while heating it to temperatures over 10 billion degrees. This creates expanding fireballs that glow more brilliantly than the hottest stellar cores, while broadcasting their explosive announcements across cosmic distances that span entire galactic superclusters. The optical brightness of peak supernova explosions can exceed the luminosity of entire spiral galaxies for weeks or months. What makes supernova explosions especially remarkable as cosmic beacons is their ability to serve as distance indicators for galaxies billions of light-years away. Certain types of supernova explosions produce such consistent peak brightness levels they function like cosmic light bulbs with known wattage. By comparing apparent brightness with intrinsic luminosity, astronomers can calculate precise distances to galaxies so remote their light has been traveling toward Earth. For most of cosmic history, these stellar explosions essentially serve as cosmic mile markers that allow measurements of universal expansion rates and the discovery of dark energy. The aftermath of supernova explosions continues broadcasting cosmic signals for thousands of years. As shock waves interact with surrounding interstellar material, supernova remnants create expanding shells of hot gas that glow with characteristic X-ray and radio emissions, while accelerating cosmic ray particles to speeds approaching light itself. These long-lived stellar death announcements can remain detectable across our galaxy for millennia after the original explosions, serving as cosmic tombstones that mark locations where massive stars once converted stellar cores into neutron stars or black holes. Inside exploding supernovae, physics operates under conditions so extreme they create natural laboratories for nuclear processes impossible to recreate anywhere else in the universe. During the few seconds of core collapse and shock wave propagation, stellar material experiences temperatures exceeding 100 billion degrees. Pressures millions of times greater than stellar cores, and neutron fluxes so intense they can build atomic nuclei heavier than iron through rapid neutron capture processes that occur nowhere else in cosmic history. The explosion mechanism begins when core bounce shock wave stall partway through stellar outer layers due to energy losses from neutrino emission and nuclear dissociation reactions. This creates a cosmic standoff where shock waves lack sufficient energy to completely disrupt stellar structure, while core collapse has already created conditions too extreme for normal stellar physics. The stalled shock wave essentially represents a cosmic Mexican standoff between gravitational collapse and nuclear explosion forces. What breaks this standoff and triggers successful supernova explosions remains one of astronomy's most challenging unsolved problems. Current theories involve complex interactions between neutrino heating, convective overturn, and magnetic field amplification that somehow revive stalled shock waves and provide the extra energy needed for complete stellar disruption. These processes create cosmic Rube Goldberg machines where core collapse triggers neutrino emission that heats shocked material. That drives convection that amplifies magnetic fields that accelerate particles that deposit energy. That revives shock waves that finally succeed in exploding the star. During the brief moments when shock waves successfully propagate through stellar outer layers, conditions become extreme. They manufacture most of the universe's supply of elements heavier than iron. Rapid neutron capture processes build atomic nuclei by adding neutrons faster than radioactive decay can remove them, creating isotope chains that produce gold, platinum, uranium, and dozens of other heavy elements. Through nuclear alchemy impossible under normal stellar burning conditions. A single supernova explosion can synthesize more gold than our sun could produce through billions of years of normal nuclear fusion. The shock wave propagation also triggers explosive nucleosynthesis that converts stellar hydrogen and helium into intermediate mass elements, like calcium, titanium, and chromium through explosive burning processes that occur in seconds, rather than the millions of years required for normal stellar fusion. These nuclear reactions essentially compress millions of years of normal stellar evolution into brief explosive episodes. that completely reorganize stellar chemical compositions while ejecting the products into interstellar space at thousands of miles per second. The final act of massive stellar death comes down to cosmic accounting, where the star's remaining core mass after explosion determines whether it leaves behind a visible neutron star remnant or disappears completely into a black hole. This cosmic either-or decision depends on whether core collapse can be halted by neutron degeneracy pressure or continues past all known physics limits toward gravitational singularity formation. The difference between cosmic visibility and cosmic disappearance hinges on core masses differing by just a few solar masses. Stellar cores between roughly 8 and 25 solar masses experience core collapse that stops when compressed material reaches nuclear density limits, around 500 million tons per cubic inch. At these densities, neutrons pack together as tightly as nuclear physics allows, creating degeneracy pressure that can finally halt gravitational collapse and create stable neutron star configurations. These cosmic ball bearings represent the densest stable matter in the known universe, objects where atomic nuclei essentially disappear and matter exists as pure neutron fluid compressed to nuclear physics limits. The neutron stars created by successful degeneracy pressure resistance possess properties that challenge human intuition about matter and gravity. A typical neutron star packs roughly 1.4 times our Sun's mass into a sphere only 12 miles across, creating surface gravitational fields 100 billion times stronger than Earth's gravity. Matter densities in neutron star cores exceed nuclear densities by factors of 10, creating states of matter that may include exotic particles like hyperons, kaons, and quark matter that exist nowhere else in the current universe. For stellar cores exceeding roughly 25 solar masses, gravitational collapse proceeds past neutron degeneracy pressure toward densities where space-time itself becomes so warped it creates event horizons, cosmic point-of-no-return boundaries where escape velocity exceeds light speed. Matter falling past event horizons disappears from the observable universe while leaving behind gravitational effects that continue influencing surrounding space-time geometry. Black holes represent regions where general relativity creates cosmic one-way valves that allow matter and energy to enter, but prohibit any information from escaping back to the outside universe. The transition between neutron star and black hole formation represents one of cosmic physics' sharpest boundaries. A stellar core with 2.5 solar masses becomes a neutron star that remains visible throughout cosmic history. An almost identical core with 3.0 solar masses disappears entirely into a black hole that becomes invisible except for its gravitational effects. This cosmic accounting system rewards stellar cores that manage their final collapse carefully with continued visibility, while condemning slightly more massive cores to gravitational exile beyond event horizons, where they become cosmic ghosts that influence the universe through gravity alone. Meet the universe's most successful weight loss champions. Neutron stars that have achieved compression ratios so extreme they make white dwarfs look like cosmic lightweights. These stellar remnants represent the ultimate in cosmic dieting, squeezing roughly 0.4 times our Sun's entire mass into spheres only 12 miles across. To put this achievement in perspective, a single teaspoon of neutron star material would weigh about 10 billion tons, equivalent to the mass of Mount Everest compressed into something small enough to fit on a dessert spoon. This cosmic compression achievement occurs through physics so extreme it challenges human comprehension of matter itself. When massive stellar cores collapse during supernova explosions, gravitational pressure becomes so intense it literally crushes atomic structure out of existence. Protons and electrons get squeezed together so violently they merge into neutrons, eliminating all the empty space that normally exists between atomic nuclei. Over hundreds of millions of years, this chemical sorting creates distinct compositional zones. The result is matter compressed to nuclear density, essentially a giant atomic nucleus the size of a small city. Neutron star surfaces create gravitational environments so intense they would instantly flatten any visiting spacecraft into atomic pancakes. Surface gravity exceeds Earth's gravitational pull by factors of 100 billion, meaning a 150-pound person would weigh 15 trillion tons while experiencing tidal forces strong enough to stretch them into cosmic spaghetti, before 10 billion degree surface temperatures completed the vaporization process. These stellar diet champions essentially create their own gravitational torture chambers, where normal matter cannot survive in any recognizable form. The magnetic fields surrounding neutron stars achieve intensities that dwarf anything found elsewhere in the known universe. Typical neutron star magnetic fields exceed Earth's magnetic field by factors of 1 trillion, creating cosmic electromagnets powerful enough to erase credit cards from distances of 600 miles, while generating electrical voltages that could power human civilization for millions of years. Some neutron stars called magnetars develop magnetic fields so powerful they can trigger earthquakes on Earth, from distances of thousands of light years through pure electromagnetic stress. Perhaps most remarkably, neutron stars maintain their extreme compression indefinitely without any external energy source to resist continued gravitational collapse. Neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same quantum state, provides structural support, strong enough to resist gravitational forces that would crush any other known form of matter. These cosmic dyad success stories represent the densest stable matter in the universe, achieving compression ratios that approach the fundamental limits of physics while remaining stable across time periods longer than the current age of the cosmos. Black holes represent the universe's ultimate gravitational magicians, performing space-time tricks so extreme they create regions where the normal rules of physics break down completely. These cosmic conjurers don't just bend light slightly like gravitational lenses. They warp spacetime so severely they create one-way cosmic trapdoors, where anything crossing the event horizon disappears forever from the observable universe. Even photons traveling at light speed cannot escape once they venture too close to these gravitational monsters. The magic trick begins with gravitational fields so intense they literally curve spacetime into impossible geometries that defy human intuition. Near black hole event horizons, space gets stretched and time gets compressed in ways that create cosmic funhouse mirrors, reflecting distorted versions of physical reality. Clocks run slower, distances become meaningless, and the concept of escape loses all physical meaning once gravitational acceleration exceeds the speed of light itself. What makes black hole spacetime magic, especially mind-bending, is how it creates different realities for different observers. Someone falling toward a black hole event horizon would experience time normally from their own perspective, but external observers would see them slowing down dramatically as they approach the point of no return. Eventually, outside observers would see the falling person freeze completely at the event horizon, while their image gradually fades and redshifts toward invisibility. Meanwhile, the falling person continues experiencing normal time flow right up until they get stretched into cosmic spaghetti by tidal forces near the central singularity. The gravitational magic becomes even more spectacular around rotating black holes that drag spacetime along with their spin like cosmic whirlpools. These rotating monsters create ergospheres, regions where space-time itself gets pulled around so violently that nothing can remain stationary relative to distant stars. Objects entering ergospheres get forced to participate in the black hole's rotation whether they want to or not, creating cosmic merry-go-rounds where normal concepts of rest and motion break down completely. Perhaps most mysteriously, black holes possess temperatures and emit radiation despite being invisible gravitational traps from which nothing can escape. Hawking radiation, named after physicist Stephen Hawking, represents quantum mechanical effects near event horizons that slowly evaporate black hole mass over time periods so vast they make stellar evolution look rapid by comparison. A black hole with our sun's mass would require 10 to the 67 years to evaporate completely, a time period so enormous that every star in the universe will have died and cooled long before even the smallest black holes finish their cosmic disappearing acts. Scattered throughout our galaxy, cosmic lighthouses beam radio signals across interstellar space with timing precision that rivals the world's best atomic clocks. These stellar beacons are pulsars, rapidly spinning neutron stars that sweep narrow radio beams across our line of sight, like cosmic searchlights rotating at speeds that would tear apart any normal object. The fastest known pulsar spins 7016 times per second, completing more rotations in 1 second than a typical car tire makes during an hour of highway driving. The lighthouse effect occurs because pulsar magnetic fields concentrate radio emission into narrow beams that emerge from magnetic polar regions rather than uniformly in all directions. As these cosmic lighthouses spin, their radio beams sweep across space like airport radar systems, creating brief radio pulses each time the beam direction aligns with Earth's position. These radio flashes arrive with such remarkable regularity that astronomers initially wondered whether they represented artificial signals from extraterrestrial civilizations trying to communicate across interstellar distances. What makes pulsar rotation so remarkably stable is the enormous rotational inertia of neutron star matter, compressed to nuclear densities. A typical pulsar contains more rotational energy than our entire solar system possesses in orbital motion. Yet this cosmic spinning top maintains rotation periods stable to better than 1 part in 100 million across decades of observation. The rotational precision exceeds that of quartz watches and approaches the accuracy of cesium atomic clocks, making pulsars some of the most precise timekeepers in the known universe. The radio beam generation process creates cosmic power plants that convert rotational kinetic energy into electromagnetic radiation with remarkable efficiency. Spinning neutron star magnetic fields generate electrical voltages exceeding 10 to the 15 volts, powerful enough to accelerate particles to speeds approaching light while creating coherent radio emission through processes that remain incompletely understood despite decades of theoretical work. These cosmic dynamos essentially operate as natural particle accelerators that produce radio beams detectable across thousands of light years. Pulsar rotation rates gradually slow down over millions of years as electromagnetic radiation carries away rotational energy. But this spin-down occurs so gradually it can be measured and predicted with extraordinary precision. Young pulsars spin faster and gradually decelerate as they age, eventually becoming too slow to generate detectable radio emission after roughly 10 million years of cosmic lighthouse operation. Some pulsars can be spun back up to rapid rotation through accretion of material from binary companions, creating recycled millisecond pulsars that represent cosmic lighthouses restored to youth through gravitational cannibalism. On August 17, 2017, humanity witnessed one of the most spectacular cosmic events in observable history. when gravitational wave detectors caught the death spiral of two neutron stars spiraling toward catastrophic collision. This cosmic car crash occurred 130 million light-years away in a galaxy so distant its light began traveling toward Earth, when dinosaurs still ruled our planet. Yet sensitive instruments on Earth detected the gravitational ripples from this collision and tracked the explosive aftermath through telescopes spanning the entire electromagnetic spectrum. The collision detection story reads like cosmic detective work where multiple types of evidence arrived at Earth within hours of each other. Gravitational wave observatories detected the characteristic chirp signature of two massive objects spiraling inward at accelerating speeds. As they lost orbital energy to gravitational radiation, the signal lasted 100 seconds and swept upward in frequency like a cosmic siren, as the neutron stars completed their final death dance before merger. Just 1.7 seconds after gravitational waves stopped, gamma-ray satellites detected a brief but intense burst of high-energy radiation from the same sky location. This gamma-ray flash lasted only 2 seconds, but released more energy than our Sun will produce in 100 million years, confirming that neutron star collisions create some of the most violent explosions in the current universe. The timing correlation between gravitational waves and gamma rays provided the first direct evidence that these cosmic crashes trigger the mysterious gamma ray bursts that had puzzled astronomers for decades. Within hours of the initial detection, telescopes worldwide began tracking a new star-like object that appeared in the collision galaxy and gradually changed color from bright blue to deep red over several weeks. This kilonova explosion represented the radioactive decay of heavy elements forged during the neutron star merger, through rapid neutron capture processes impossible under normal stellar conditions. Spectroscopic analysis revealed clear signatures of gold, platinum, and other precious metals, created through nuclear alchemy occurring only during these cosmic collisions. The scientific treasure trove from this single neutron star merger detection revolutionized multiple fields of astronomy simultaneously. Gravitational waves provided direct measurement of cosmic distances independent of traditional methods. Gamma-ray timing confirmed that gravitational waves travel at light speed as Einstein predicted. Heavy element detection solved the long-standing mystery of where the universe manufactures gold, platinum, and uranium. Multi-messenger astronomy, combining gravitational waves, electromagnetic radiation, and particle detection, opened entirely new windows for studying cosmic events that remain invisible to traditional telescopes. Some white dwarf stars refuse to retire gracefully into cosmic obscurity and instead become stellar vampires that slowly drain material from nearby companion stars until they trigger nuclear explosions so violent they completely destroy themselves. These cosmic cannibals represent stellar retirees gone rogue, objects that should be cooling quietly for billions of years but instead choose paths towards spectacular self-destruction through gravitational theft and runaway nuclear burning. The vampire process begins when white dwarf stars find themselves in close binary relationships with normal main sequence companions. White dwarf gravity gradually strips material from the companion star's outer atmosphere, creating streams of hydrogen-rich gas that spiral inward toward the white dwarf surface like cosmic drain water. This stolen material accumulates in hot, dense layers on the white dwarf surface, while being compressed by gravitational fields 100,000 times stronger than Earth's gravity. As stolen hydrogen accumulates on white dwarf surfaces, temperatures and pressures climb toward critical thresholds for explosive nuclear burning. Unlike normal stellar cores where nuclear fusion proceeds gradually under controlled conditions, White dwarf surface layers experience sudden nuclear ignition. When hydrogen concentrations reach critical levels, the compressed stellar material burns so rapidly it creates thermonuclear explosions. That can temporarily increase white dwarf brightness by factors of 100,000 or more. These stellar vampire explosions come in two distinct flavors with dramatically different outcomes. Nova explosions occur when hydrogen accumulation triggers surface nuclear burning that blows away accumulated material, while leaving the underlying white dwarf intact to repeat the vampire process. The white dwarf essentially survives its own nuclear tantrum and continues stealing material for future explosive episodes. That can repeat every few decades or centuries. But when white dwarf vampires manage to accumulate enough stolen material to approach the critical mass limit of 1.4 solar masses, they trigger Type 1a supernova explosions that completely annihilate the entire white dwarf structure. These cosmic self-destruction events occur when nuclear burning becomes so intense it propagates throughout the entire white dwarf mass within seconds, converting stellar material into iron peak elements while releasing energy equivalent to 5 billion times our sun's luminosity. The explosion completely destroys the vampire white dwarf while creating expanding debris clouds that remain visible for thousands of years as monuments to stellar greed. When stars die through gentle planetary nebula formation or violent supernova explosions, they don't simply disappear from cosmic history. They become the universe's most generous philanthropists. They donate their entire chemical wealth to future generations of stellar and planetary construction projects. Every element heavier than hydrogen and helium in the known universe represents inherited stellar material. It is distributed through space by dying stars that spent millions or billions of years cooking raw hydrogen. They cook it into the chemical diversity needed for planets, oceans, and living creatures. The cosmic donation process operates through stellar winds and explosive mass ejection. These scatter process stellar material across vast regions of interstellar space. During red giant phases, aging stars develop powerful stellar winds that carry away their outer atmospheric layers. They move at speeds of 10 to 100 miles per second. These gentle stellar breezes gradually distribute carbon, oxygen, and nitrogen throughout local galactic neighborhoods over millions of years. Meanwhile, supernova explosions violently eject stellar material at thousands of miles per second. They create expanding shock waves that can distribute heavy elements across hundreds of light years within just a few thousand years. This stellar charity work has been operating continuously for over 13 billion years. It gradually enriches the galaxy's chemical composition through successive generations of stellar death and material redistribution. The early universe contained only hydrogen and helium. First-generation stars had not yet time to cook heavier elements. They also had not yet distributed them through stellar death processes. Modern interstellar space contains rich mixtures of carbon, oxygen, silicon, and iron. This is because billions of stellar generations have lived, processed nuclear fuel, and donated their chemical products to the Galactic Recycling Program. The donation efficiency varies dramatically depending on stellar mass and death style. This creates different contributions from different types of stellar benefactors. Modest stars like our Sun will eventually donate roughly 30% of their mass through planetary nebula formation. They contribute primarily carbon, nitrogen, and oxygen to the cosmic charity drive. Meanwhile, massive explodes as supernovae and donate up to 90% of their mass. They contribute the galaxy's entire supply of elements heavier than iron. This happens through explosive nucleosynthesis that occurs nowhere else in cosmic history. Perhaps most remarkably, this stellar donation program operates with perfect cosmic recycling efficiency. It wastes nothing and reuses everything across multiple generations. Heavy elements scattered by dying stars eventually get incorporated into new stellar formation regions. There, they become raw materials for planetary construction projects and biological chemistry. The calcium in your bones, the oxygen you breathe, and the iron in your blood all represent donations from ancient stars. They died billions of years ago. Every atom in your body except hydrogen represents stellar charity that connects you directly to cosmic history. Supernova explosions don't just destroy massive stars. They also serve as cosmic matchmakers. They arrange marriages between gravity and gas clouds to create new stellar families. The powerful shock waves racing outward from exploding stars compress nearby interstellar material. They trigger gravitational collapse in gas clouds. These clouds might otherwise drift peacefully through space for millions of years without ever forming stars. These explosive stellar deaths become cosmic fertility treatments. They dramatically increase stellar birth rates throughout their galactic neighborhoods. The cosmic midwife process begins when supernova shock waves traveling at 10,000 miles per second slam into interstellar gas clouds. These collisions compress gas densities by factors of 100 or more. They also create turbulent motions. This helps overcome magnetic pressure and thermal support resisting gravitational collapse. What was once a stable, diffuse gas cloud suddenly becomes gravitationally unstable. It begins fragmenting into multiple stellar nursery sites. This shock-triggered star formation creates cosmic baby booms. It can increase stellar birth rates by factors of 10 to 100 throughout entire galactic regions. A single supernova explosion can trigger formation of hundreds or thousands of new stars. This can happen across volumes spanning hundreds of light years. These stellar fertility treatments convert explosive stellar death energy into gravitational potential energy. That powers the next generation of stellar construction projects. It also ensures continuous stellar population replacement throughout galactic history. The timing of shock-triggered star formation creates cosmic family trees. Stellar generations are connected through direct cause and effect relationships spanning millions of years. Massive stars live fast, die young through supernova explosions, and trigger formation of new stellar families. These form from shock-compressed debris of their explosive deaths. Some of these newly formed stars will become massive enough to explode as supernovae within 10 million years. This continues the cycle of death-triggered birth that has operated throughout cosmic history. What makes this cosmic reproduction cycle especially elegant is how it naturally regulates stellar birth rates. It depends on the availability of heavy elements and gas supplies in different galactic regions. Areas with recent supernova activity experience enhanced star formation. They also receive fresh supplies of heavy elements needed for planetary formation. Meanwhile, regions without recent stellar deaths gradually exhaust their gas supplies. They reduce star formation rates until new supernova events arrive to restart the cosmic fertility cycle. Our solar system represents a cosmic inheritance story. It spans billions of years and dozens of stellar generations that lived, died, and donated their chemical wealth. They contributed to the gas cloud that eventually collapsed to form our sun and planetary family. Every atom in Earth's oceans, atmosphere, and rocky structure except hydrogen represents processed stellar material. It was contributed by ancient stars whose names we'll never know. Their chemical gifts make our existence possible. The inheritance timeline begins roughly 9 billion years ago. First-generation massive stars in our galactic neighborhood began exploding as supernova. They distributed the universe's initial supply of carbon, oxygen, silicon, and iron into local interstellar space. Successive waves of stellar death gradually enriched our cosmic neighborhood with increasingly diverse chemical elements. Supernova shock waves stirred and mixed this stellar material. This happened throughout volumes spanning hundreds of light years. By 4.6 billion years ago, the gas cloud destined to become our solar system had accumulated chemical contributions from an estimated 30 to 100 previous stellar generations. This cosmic inheritance included basic elements like carbon and oxygen. It also included trace amounts of exotic heavy elements like gold, platinum, and uranium. These are created only during supernova explosions and neutron star collisions. Our pre-solar nebula represented a chemical museum. It contained samples from billions of years of galactic stellar evolution. The evidence for this cosmic inheritance story can be found throughout our solar system. It appears in isotopic signatures that record the nuclear fingerprints of different stellar sources. Meteorites contain tiny grains of presolar material. These are microscopic fossil remains of ancient stars. They survived solar system formation and can be analyzed in terrestrial laboratories. These stellar fossils reveal isotopic compositions that match theoretical predictions. They match material processed inside red giant stars and supernova explosions. They also match exotic stellar environments like Wolf-Rayet stars. Perhaps most poetically, the chemical diversity that makes Earth a habitable planet derives from this ancient stellar inheritance program. It supports oceans, atmosphere, and biological complexity. The silicon and iron that form rocky planetary cores came from massive stars that exploded as supernovae. The carbon and oxygen essential for biological chemistry were donated by intermediate mass stars during their red giant phases. Even the water molecules in Earth's oceans show this collaboration. They contain hydrogen from the Big Bang, combined with oxygen manufactured inside stellar cores. That oxygen was distributed through planetary nebula formation. Our planetary ecosystem reflects a cosmic collaboration between dozens of stellar generations. Their combined contributions created the chemical foundation for life itself. Every breath you take connects you directly to stellar explosions that occurred billions of years before Earth even existed. The oxygen filling your lungs was forged inside the nuclear furnaces of massive stars. They died when our galaxy was young. The calcium strengthening your bones was manufactured during supernova explosions. These distributed heavy elements throughout cosmic space. Most remarkably, the iron flowing through your circulatory system was created during the final seconds of stellar core collapse. Your blood contains material forged during some of the most violent events in cosmic history. This cosmic family tree extends far beyond the basic elements essential for biological chemistry. The carbon forming the backbone of every protein and DNA molecule in your body was cooked inside stellar cores. This required helium fusion at temperatures exceeding 100 million degrees. The phosphorus in your DNA and cell membranes represents stellar material. It was processed through oxygen-burning phases that occur only inside massive stars during their final years before core collapse. Even the trace amounts of iodine essential for thyroid function were created through rapid neutron capture during supernova explosions. The timeline connecting stellar nucleosynthesis to human biochemistry spans most of cosmic history. It involves contributions from multiple types of stellar death processes. Lighter elements like carbon, nitrogen, and oxygen were contributed primarily by intermediate mass stars. These died as planetary nebulae during the galaxy's first few billion years. The iron in your blood required supernova explosions throughout galactic history. Successive generations of massive stars lived fast, burned bright. and exploded to distribute iron peak elements. Some trace heavy metals in your body also have rare origins. Tiny amounts of gold were created during neutron star collisions. These events are so rare they occur only once per galaxy per million years. Perhaps most mind-boggling, the nuclear processes that created your body's elemental composition operated under conditions that cannot be recreated today. They occur now only during stellar death events. The iron atoms in your hemoglobin experienced temperatures exceeding 3 billion degrees. They also experienced pressures millions of times greater than Earth's core during formation in collapsing stellar cores. The gold atoms in your body survived neutron densities approaching nuclear physics limits during neutron star collisions. These collisions created gravitational waves detectable across intergalactic distances. This cosmic ancestry means human existence depends on a 13 billion-year sequence of stellar birth, evolution, death, and chemical redistribution. It transformed the universe's initial chemistry into the molecular complexity needed for biological evolution. You are literally made of star stuff. That is not a poetic metaphor. It is a demonstrable scientific fact. It connects your physical existence to cosmic processes spanning the entire history of the universe. Every element in your body heavier than hydrogen represents a stellar memorial. It carries the nuclear signature of ancient stars. Their death enabled your life through cosmic chemical inheritance. This links biological complexity to stellar sacrifice across billions of years of galactic evolution.